According to the internet, the mean length in seconds of a radio song is 235. Assume the data follow a normal distribution with a standard deviation of 45. Consider for a moment the second sentence there. Why is it important that the data follow a normal distribution? The answer is really in the problems A and B, and maybe E and F. But it's so that we can use the central limit theorem results. The central limit theorem results, which are very, very important. They are very important. There are a number of theorems out there in the world, a number of them, and they have different results. One that I like this one a lot. This is not the central limit theorem. This is the Pythagorean theorem, right? So think about what the result is of that, right? It's that all triangles add up to be some degrees, right? Whatever it is. That's the result of that, right? The central limit theorem, the results are the following, which is the highlight really of the course. See, everything falls back on this because we no longer care about how x behaves. It's how does x bar behave? So here are the results of the central limit theorem. There's a few of them. It's that the distribution of the sample means will follow a normal distribution. And what that means is usually we'll be within 2 standard deviations of the truth. Now, the central limit theorem says if x is normally distributed, it doesn't matter if you have a sample size of 4, 5, 6, 7, 8, 9, 10. No matter what, you're going to have a normally distributed distribution of sample means. So, in other words, when sample size is smaller, 30 is the cutoff, reasonable cutoff. When we have a small sample size, we want to assume the data are normally distributed in order to use the results of the central limit theorem. If the data are not normally distributed, we just have to have a sufficiently large sample size because that's really where the power of the central limit theorem comes in. Here's another case. We'll call this case 1. Case 1. This is case 2. Here's case 2. Put x and then x bar. And put that here. Put the mean in the middle. All right. And then here's the distribution of x. Start there and then move over like this. Right? The idea is it doesn't matter. That's a question mark. It doesn't matter how x behaves. You're always going to get a normal distribution if... Very exciting. Very exciting. You're always going to get a normal distribution if your sample size is large enough. Now the question is, this is a pronoun game. You're always going to get a normal distribution. So it will be normally distributed. What is it referring to? It is no longer referring to x. It is referring to x bar. X equals the length of a song. Right? Turn on the radio right now. Time it. It's one song. It's going to give you a length, a piece of data. What you're interested in knowing is, what about the sample of the next 4 songs? So what you're going to do is calculate a statistic x bar. How is that statistic going to behave? It's going to follow a normal distribution. Who is it? See? A normal distribution. A normal distribution. With a mean equal to the original population mean come on. A mean equal to the original population mean, which is another result, which I threw in there in those two cases. Probably a more efficient way to erase here, but what are you gonna do? That's how it goes. It's the way she goes. All right, so okay, so the central limit theorem, here's the primary result. Let's set this up here. X follows one of these distributions. Whoa! That distribution, one of those. That's okay. The distribution of sample means will be approximately normal with a center at the true mean. That's the result. The mean of the means is the mean. It's not shocking, right? If you think about all the songs that are played on the radio today, and you add up all those songs, the length, and then divide by the total, you're going to get mu, the true mean for the day. If you started sampling 4 at a time and then just averaged all those together, you're going to get the true mean. That's the result, right? That's the result of the central limit theorem. That's one of the results. So I'm going to write that down here. Mu. So that's the population mean equals the mean of the sampling distribution of sample means. We put a subscript x bar because that's just saying, hey, it's the probability distribution of x bar now, right? That result is not that big a deal, although it is a huge deal, as we'll see very shortly, because instead of mu, when we get to hypothesis testing, we're just going to put a value that we're hypothesizing in there, okay? But the result that really matters to me, in particular, is this idea of how much variability is there. How much variability is there? And the answer is, this comes from the central limit theorem. This is very much like the Pythagorean theorem in that it's a result. It's incredible how it happens. But if you take the population standard deviation divided by the square root of the sample size, you will get the variability in the sampling distribution of the sample means. So this term right here is the mean of the sampling distributions of sample means, right? Mouthful, but here's a real mouthful. The standard deviation of the sampling distribution of sample means. It's too much. We say standard error. Standard error. Okay? The larger your sample size, the smaller your standard error is going to be. For instance, let's say that we had a sample size of 30. Here's 30. N equals 30. That's in red. Now what I'm going to do is draw the sampling distribution for a bigger sample size. Think about how the standard deviation divided by the square root of the sample size is going to be affected, everything else remaining the same, if you just increase the sample size to, how about 1,000. Here we go. Whoa! Like, look how skinny that normal curve is. The reason why is because instead of doing sigma divided by the square root of 30, you're doing sigma divided by the square root of 1,000. Right? That number on the right is going to be much, much, much smaller. So in part A, if n equals 4, what would the z-score be for x bar equals 224? And then C, it says, what about if n equals 100? So think about doing A and C together. And then ask yourself, for A and C, which one will be weirder? Would it be weirder, like the true mean length of a radio song is 235 seconds. What would be weirder? The idea in part A, the event in part A, or the idea in part C? Until next time.